Let's look a little closer at the pH scale. So we know that solutions can be acidic, basic, or neutral. What that means is in a neutral solution, you have your hydronium ions equal to your hydroxide ions as seen in this first scale. And so there's not more or less of either of them, instead it is neutral. So your pH is reported as pH of 7. If you have more hydronium ions than you do hydroxide, then the scale is tipped toward the hydronium ions and it is a low pH. So anything less than 7 is considered acidic. And then in a basic solution, now your hydroxides are tipped to the right, therefore our scale is tipped here higher, tipped to higher pHs. Anything with a pH greater than 7 is considered basic. And so really when we're looking at the question of whether a solution is acidic, basic, or neutral, we're asking what is the pH, which is completely dependent on how much hydronium ions are in solution and how many hydroxide ions are in solution. Let's look at hydrangeas as an example of a natural pH tester. So I didn't know this for the longest time, but there's two types of hydrangeas. You have those that can turn pink or blue, or if they're in the middle, they can turn purple. And then you also have your white species. The species that are changing colors, they will tell you how acidic or basic the soil is. So meaning, if your soil has a pH of 6.5 or higher, you will have pink blooms. If it's lower than 5.5, you will have blue blooms. And if you have a pH somewhere between 6.5 and 5.5, then your flowers will actually be those pretty purples that you see, or some blooms will actually be pink and some will be blue, depending on which area the roots are dipping into within the soil. And so with this, those that are your pinks, those are going to be your hydroxides, those are going to be your blues, are going to have more hydronium ions. But it's all relatively speaking, because once again, we're still looking at a pH that is less than 7 for either of the species. Alright, so even as we're looking at your pH scale, everything is on the scale somehow. So it goes on the scale on the right, looking at household items, anywhere from battery acid, which a pH of 0, all the way up to oven cleaner, which is very basic. You can see everything along the way has a acidity or a basicity, or it's a neutral sample. And so when we're talking about the pH scale, all we're saying is, hey, is this solution acidic or is it basic? And so with that, you get lots of fun math like you see here, where the pH literally means negative log of your hydronium ions. That's the same thing as negative log of your hydrogen ions. We will use those interchangeably in this lecture. And then pOH literally means negative log of hydroxide. P stands for negative log. Now some things to notice are the pH scale is a logarithmic scale. That means for every one change in pH units, you get a 10-fold change in your hydronium ion concentration. So for instance, if a pH of 4, it's represented by 1 circle, then a pH of 3, you're going to have 10 times that one. A pH of 2 would be another 10 times the previous representation. So now it's at 100. And that's because when you're looking at 10 to the negative 4, it's looking at 0.0001. That's tiny. And then if you take 10-fold times that, 0.001, and another 10-fold, 10 to the negative 2 gives you 0.01. So remember, these are exponents that you're looking at, and these are very small numbers. So whenever you have 1 times 10 to the negative 3, that is a very small number. And so keep in mind that these are all things that are less than 1. Alright, one way to quickly go back and forth between the pH scale and your hydronium ion concentration is that if it is 10 to the negative 5, that means it's related to a pH of 5. So these exponents, if you just look at them, and if your exponent's around 3, then the pH is around 3. If your exponent's around 11, then your pH is 11. And so this is a quick way to kind of get you in the ballpark of what approximately is the pH. Now there's always a number in front of it, so it'd be like 3.5 times 10 to the negative 4. That's going to change it slightly as to is it going to be 4 point something or 3.9 something. Okay, but this will get you in the ballpark, and that's how they're related. So I wanted us to practice a little bit with pH scale calculations because I know this can sometimes be tricky for students. And so we're going to do a whole bunch of examples just going from pH to POH to hydronium to hydroxide and then back and forth, back and forth. And so these are the main equations that allow you to go back and forth. Now it's basically the exact same equation. Some of them are just written mathematically arranged for you. So meaning pH equals negative log of hydronium ion. If you solve for hydronium ion, the math tells you that hydronium ions equals 10 to the negative pH. It's the same equation, it's just rearranged. So with every one of these entities, you can go back and forth between them. Okay, except for you can't go directly from POH to hydronium, and you can't go directly from pH to hydroxide. You have to stop somewhere in the middle. So we are going to use all of these equations and practice going back and forth between all of the scales that we are looking at today. And this will really just help us get a better appreciation for what's happening whenever we're talking about the pH scale or soil chemistry or something like that. Alright, so our first example, I want us to fill in this table. And so with this table, our pH is 3.75. I want us to solve for POH, hydronium ions, and the concentration of hydroxide ions. From this one value, we can get every other aspect of this table. So how do we do that? Let's first do this first part here of the table. Let's go directly from pH to POH. Now, these are the main equations that are governing the interaction between the two entities. But if we're solving for POH, let's use the one I've already solved for you. POH equals 14 minus pH. So that is 14 minus our pH, which was given to us of 3.75, which means POH is 10.25, aka 14 minus 3.75. So we can fill that in for our table. Next, I kind of like going directly from now that I've solved for POH, let's go directly to hydroxide. You can do it in any order you want. We could have started out with the hydronium ions. It doesn't matter. You just need to get all of them filled in. So with this one, I'm going to do this next. I'm going to solve for hydroxide. So if you notice, hydroxide equals, I have this equation that I can solve for. If I were going the other direction, going from hydroxide to POH, I would have used this top equation. So hydroxide equals 10 to the negative POH. We just figured out our POH, which was 10.25. So if I type into my calculator 10 raised to the negative 10.25, I will get my concentration of hydronium, or of hydroxide ions. And now I have a couple options. I can either solve for hydronium ions by taking 10 to the negative pH, or I can solve by taking 1.0 times 10 to the negative 14 and dividing it by the concentration I just found. You can do either. Let's start out first by taking 10 to the negative pH, which is 10 to the negative 3.75. When I type that in my calculator, I get 1.8 times 10 to the negative 4. I alternatively could have also written 1.0 times 10 to the negative 14 divided by 5.6 times 10 to the negative 11. Let's correct that to 1.8 times 10 to the negative 4 instead of 10 to the negative 14 as was shown a second ago. So your hydronium ion concentration is 1.8 times 10 to the negative 4. My hydroxide ion concentration is 5.6 times 10 to the negative 11, and my POH is 10.25. From my one value, I was able to solve for each of the other ones. Alright, now let's solve for the pH, the hydronium ion concentration, and hydroxide. I'm going to start out with the pH. So, when I can look at these, I need to first figure out which equation should I use. There is one equation that solves for pH, so I'm going to use this one. pH equals 14 minus 7.9 to give me a pH of 6.1. Now I have many options as to where I can go next. I'm going to go to hydroxide. You could also have gone to hydronium. It really doesn't matter. So hydroxide, if I'm going to solve for it, I could go from my POH. I can't come from here because I haven't solved that yet. So hydroxide ion here equals 10 to the negative POH, which is 10 to the negative 7.9, which is equal to 1.3 times 10 to the negative 8. And now I can do the same as prior, where I'm solving for hydronium ion by saying hydronium equals 10 to the negative pH, solve for hydronium, which gives me 7.9 times 10 to the negative 7. And so these are a couple examples of how you can go from pH or POH to your concentration of your ionic species. Let's do another one together before I ask you to do one by yourself. So for this one, in order to get to hydroxide, I have to look at this bottom equation here because I can only connect it to hydroxide. I can't connect it to POH yet because I haven't solved for POH. And so doing so, I've got hydroxide equals 1 times 10 to the negative 14 divided by hydronium ions, which is 1.0 times 10 to the negative 14 divided by 1.2 times 10 to the negative 4 to give me a hydroxide concentration of 8.3 times 10 to the negative 11. Next, I can go from hydronium ions to pH by taking pH equals the negative log of my hydronium ions. And so this is this relationship here. Okay, that solves for a pH equals to 3.9. Next, I can solve for POH by either taking 14 minus pH or POH equals negative log of hydroxide. Either way, you'll get the same answer of 10.1. Alright, now I want you to do this next example on your own. Try and complete it. Figure out which equations you can use and then type them into your calculator and see if you get these answers. So pause it and then come right back to it. And you should have gotten a pH of 6.5, a POH of 7.5, and hydronium ion concentration of 2.9 times 10 to the negative 7. Some good way to check and see if you did them all correctly is the pH plus the POH should always equal to 14, and if you add up your exponents here should equal approximately 14. Notice they're 15 here, sometimes they'll add up to 13, but they need to be in that ballpark or something went wrong with your calculator usage. With that, I'd like you to go read the final sections, sections 7.7 and 7.8 from this chapter.